We're today going to hear more practical things. Hopefully you'll find it useful.
Okay, so yesterday I basically introduced the Seidel polynomials, and I've explained how they can describe a quite intuitive way aberrations of an optical system. And we have found using the Marshall variant, we have put some tolerances on the maximum amplitude of the wave aberration. Okay, now, as I said yesterday, the problem is that the Seidel polynomials are not orthogonal. This is a problem. I'm going to ask you a question. This is 2D space, and I give you two vectors. U and V. And so this is actually describes a 2D and space of polynomial. And I give you this vector. This is some vector that will describe your waveforms. And I ask you the following question. What are the coordinates of this orange vector on the basis UV? I guess all of you think, well, I mean, it's more or less obvious, right? The coordinate of this vector on this axis is about that long. Okay. The coordinate of this orange vector on this axis is, well, about that much. Right? It doesn't deviate too much. Am I correct? Well, I'm totally wrong, because I didn't, my question is not sufficient. I didn't specify the scalar product I'm going to use in this space. I didn't tell you that these two vectors are orthogonal or not. They may be orthogonal depending on the scalar product I'm using in this 2D space. But actually now I'm going to specify my question and tell you the scalar product is such that two vectors are orthogonal if they are like this. Okay? So, if that is the case, then, well, the coordinate of this vector on U, you get it by saying, well, let's call this vector, I don't know, x, okay? Well, x is equal to lambda U plus beta V, right? And so if you want to have the coordinate along U, what you do is x U, right? You get lambda. That's actually true if you just forget about this part. Because actually, this is what it is. So in other words, you have to project on this direction, and V scalar U is not equal to 0 because they are not orthogonal. So actually, V has a strong component on this axis. And so if you try to decompose your wavefront on a basis of polynomials that are not orthogonal, the decomposition of this wavefront highly depends whether you decompose it up to the third order, let's say this is the third order polynomial, or if you wish to decompose it up to the fifth order, this is the fifth order. Okay. So, I mean, it's kind of simple, you know, it's just the problem of using an orthogonal basis in space. Zernike thought about that, and he said, in order to produce a basis of polynomials that are orthogonal, how much of U should I add to V to have a basis of polynomials that are orthogonal? Well, the answer is that's right. You add as much as something to erase.
Is it maybe it's not? There's not one hiding behind the.
Yes. Well, then you have to add as much of U such that actually you get V prime, which is V minus some quantity of U. Okay? Okay. This problem is related to the problem. Well, so I'm giving an example here. You ask yourself the question, yesterday we saw what is spherical aberration. But we ask ourselves, find a point B prime in space such that where the Strehl ratio is maximum. So that is, where is the point in space where the intensity is maximum. And we saw yesterday that maximizing this quantity is equivalent to minimizing the standard deviation of the wave aberration. So Zernike says, okay, the wavefront, so U here is the normalized aperture value, okay, normalized to the marginal height. So it varies between -1 and +1. So Zernike says the wave aberration is equal to, well, the Seidel aberration. Remember, that's amplitude times h over hm to the power 4. And he adds a little bit of this term, which you remember is the defocus term, right? And he asks himself the question, by how much defocus should I add to this Seidel aberration in order to minimize the variance of the standard deviation delta? Well, you do the calculation, it's 2 lines, and you get the following answer. You should add as much as, you should subtract as much as the amplitude of spherical aberration, of the Seidel spherical aberration. So that in the end, you get delta. I could start here to say this is the optimally balanced polynomial, the one that is such that the derivative here is equal to 0, the one that minimizes the variance. Delta star is then equal to this times U4 minus U2. If you calculate the variance of that, you find that it is equal to 1/4 of the standard deviation of the wave aberration calculated with respect to the paraxial sphere, the sphere that is centered on the paraxial edge. Okay, to say it differently, let me do another drawing. To say it differently, suppose you have an optical system, and here is the paraxial edge, and here is actual image. And now it was spherical aberration. What does that mean? It means that the weight aberration is equal. It's like this, right? It sticks well to the sphere here, and here it strongly deviates. Okay? Orange curve is not a sphere. Now, delta max, the peak value, the zidal amplitude, is this quantity here. But you ask yourself the question, where, obviously it's on axis, where on axis do I have a maximum intensity? The answer is, well, it is maximum if the standard deviation of the wave aberration around the sphere that is centered on that point is minimal. And I'm going to draw it. It's here. Here is the sphere. It goes through these three remarkable points. Draw a sphere through these three points. It is centered, so here I missed, right? Here. This is a best focus, a prime best focus. By this I mean, this point is such, and this sphere, let's call it S star. This sphere is such that the variance of the wavefront sigma around this blue sphere, so the variance is the integral of the square of the differences. I'm going to shade it. This variance is minimum. If you move this way, it's going to increase, and thus the intensity will decrease. If you move this way, same thing.
So it sounds like, it seems a little surprising that it's the circle defined by the optical axis and just the marginal rays, that would give you the lowest variance. Would it be obvious that that's the right answer?
It is surprising that it's only the marginal rays.
The way you've drawn it, the only points that matter are the axis, the optical axis, and the marginal ray.
Right.
And
yes. I'm trying to understand why this is surprising.
Well, you've drawn a shaded area that essentially you're trying to minimize.
Right.
So I would think that if you deviated, if the blue area went on both sides, you might get a lower total area.
No, it's not the area, it's the square. It's not the area.
Okay.
And this increases if you deviate from that. Well, that's what the calculation says. And I'm trying to convey a picture. Okay, so, well, basically what I have represented here is the same story. I have represented the optical path difference. This is the Zidal polynomial, this one. And this is delta star, the one that has the minimum variance. I mean, the question says, if you defocus a little bit from there, for instance, this is going to go up, and we would get something like this. Well, what the calculation says is that the variance of this new curve will be larger than this one, and the other way around too.
And the endpoints are the marginal rays through the system.
Yes.
Okay.
Yes. Well, which, by the way, means also that if we decrease the diameter of the iris diaphragm, the best focus moves. And, of course, ultimately, if the iris diaphragm is totally closed, the best focus is here. Right. So this was to illustrate what Zernike did, and I illustrated it on the spherical aberration. this polynomial is called a balanced polynomial because it is a Zidal spherical aberration balanced by some defocus, the right amount of defocus such that the variance is minimal, so that the Strehl ratio is maximum. And it is optimally balanced. Now, you see that doing this, using this trick, I have relaxed the tolerance on this amplitude. You can, since the Strehl ratio should be larger than 80%, it puts a new constraint on the maximum spherical aberration you can get, right? And since the calculation leads to a factor of 1/4, it means that you can increase by factor 4 the amplitude of your spherical aberration. We saw yesterday that the maximum Zidal spherical aberration you could have is 0.24 lambda times 4. That's 0.96 lambda. Okay. So actually, you can get as much as that, provided you put your CCD at the right point. Okay, there. Okay. So Zernike, who by the way got the Nobel Prize in 1953 for the phase contrast microscope, introduced a basis of optimally balanced and normalized polynomials, and he made these. He started from the Zidal polynomials, and he built up a basis of polynomials that are orthogonal on a circular pupil. It's important to remember this because, for instance, if you try to find a basis of polynomials that are orthogonal on a pupil that is not a disk, this is not that. Okay. For instance, if you use a telescope, you know that the telescope has usually a central mask, right? And so the pupil is actually annular. Well, so then the basis of polynomials that is well adapted to describe the problem is not the Zernike. Okay, I'm not going through all this, right? This is just to show you that they are well known and they've been built seriously. And just a few words. Z like Zernike, N, M. The M here says that this polynomial varies like cosine M phi. No surprise. We introduced cosine M phi yesterday, also with the Zidal polynomials. There is some normalizing factor here. Let's forget about it. Depends on N and M. But most importantly, here you've got a polynomial that, well, that depends on U. It's a polynomial of degree N, and it contains terms like, or if I take here R31, well, it's U3 and U. Spherical aberration would contain U4 and U2, the one I just introduced before. Spherical aberration of a fifth order, just to have fun. Fifth order means the polynomial would be of the sixth order. It's spherical aberration, doesn't depend on phi, doesn't depend on the field. So what is that? What kind of polynomial is that? The Zidal fifth order spherical aberration is delta of U equals, yeah. Well, Zernike says, how much of the third order spherical aberration should I add to this fifth order Zidal spherical aberration so that my modified polynomial would be orthogonal to the third order spherical aberration? And by the way, also, by how much defocus should I add to this polynomial so that it is also orthogonal to the defocus? Well, same story, right? It's just now you're in the 3D space. So That's why, so the answer after calculation, the answer is, well, R60 describes the fifth order spherical aberration. It is a combination of U6. I have to subtract a little bit of spherical aberration of the third order. I have to add a little bit of defocus. And well then. Okay. So, for a centered system, that is a system that has an axis of revolution, you can decompose the wave aberration on the Zernike polynomials. And these are the coefficients. And note that Zernike's problem was, I've got a telescope, and I've oriented the telescope to see that part of the sky. And so the positions of the stars are known and fixed, so the object is fixed. And so it's hidden inside here. So he gives a decomposition of the wave aberration only as versus the aperture variables, u and phi. Okay, for a non-centered system, he says, well, the polynomials I introduced before do not make a complete ensemble of polynomials. It's not the basis. I have to complete this ensemble by other polynomials that include sine and whatever. And in the end, well, here is, I stopped at some point, okay? I just gave you some polynomials up to the fifth order. So, here we are. These are, well, piston, tilt, defocus. Actually, piston should be orthogonal to all the other polynomials. Piston is a constant, okay? So it means that the average of all the other polynomials should be 0 in order to be orthogonal to the first one. Astigmatism, comma, one I've just shown, spherical aberration. Well, and then we keep going, and they have fancy names because it varies by 3 phi, so they call them trefoil. Okay, good. So now, what do they look like? Well, tilt looks like the zygote. Defocus, well, defocus is U2 minus a constant to be orthogonal to the piston. So if you look carefully here, 0 is not at the bottom here, 0 is here, so that the average of this polynomial is 0. A saddle remains a saddle. A chair becomes an armchair. A chair like that is being relaxed into an armchair. I've removed the right amount of tilt, U3 minus U. I've removed the right amount of tilt such that the variance of that polynomial is minimum. This is the sister polynomial of this one, turned by 90 degrees. Okay, it's orthogonal to this one. Our friend, the third order spherical aberration. Well, now it's got a donut shape. The external parts of the polynomial vary as U4. And here, you've got balancing by some defocus. Okay, so this here is parabolic in the center. And so on. Okay, where is trefoil? Trefoil. It has a threefold symmetry. Okay? So where is it? Yeah, there, great. Okay, this is important because Palaiseau is very expensive. But a Shark Altman wavefront analyzer is much cheaper. And so maybe you can buy one and use one. And a Shark Altman would decompose your wavefronts on the basis of the Zernike polynomials. Okay? So it means in the end that you send your beam in the wavefront analyzer, and you get tables of coefficients. Now you know what these are. Okay? These are the coordinates of my wavefront on this basis. Now, yeah.
Can you write down the name of that analyzer, the wavefront analyzer?
Sure. Oh, sorry. Two different guys. Now, this was, making the basis of polynomials orthogonal was very clever, because I didn't say, but of course, the scalar product that I'm using is the natural scalar product of two polynomials over a circular basis. It's the integral over the QL of two polynomials. And this integral is 0 if n differs from n prime and n differs from n prime. And it's equal to a constant, pi, if there's a sign. And so going from here to there is just one-line calculation. You calculate the integral of the square. You take your wavefront, as I said before, you plug it inside this integral, and all the cross terms vanish because the polynomials are orthogonal. And so in the end, what you get is that the variance of the wave aberration is just the sum of the squares of all the coordinates. Well, this is very powerful, because it says, what it says is that thanks to this orthogonalization procedure, aberrations add quadratically to degrade the Strehl ratio. This is totally consistent with what Zernike wanted to do. How do you find the best focus? You move in space, you move your CCD in space such that you find the maximum intensity, so that you minimize the variance. What does that mean here? It means that you move it around such that you cancel the terms that correspond to defocus, and the terms that correspond to tilt. Okay. The terms corresponding to defocus are C20, and the terms corresponding to tilt are C1 and C minus. And once you are at the best focus, well, you can't help. The remaining aberrations are there, and you've got to deal with it. So, new tolerances, relaxed tolerances. This is the old basis. This is the tolerances at the best focus. We said we already saw this. Well, you see that you also relax the tolerance for coma, for astigmatism. Well, field curvature, here there's nothing. Why? Just because it's nonsense. Because field curvature, again, means that what is field curvature? Means that you send light with an angle theta with respect to the axis, And oops, light doesn't focus in the paraxial plane. So, where should you put your camera in order to maximize the intensity? There. And then what's the tolerance on your field curvature once you're there? Well, there's no tolerance, as much as you want, actually. If you put more field curvature, just move more. The best focus is where it's maximum. You can have as much field curvature as you want, provided you move by the right amount. Same thing for distortion. Okay. Good. So basically, I just want to show now a few pictures of what's going on if you have only a geometrical approach or if you have diffraction approach. And I took on purpose examples where it's not easy to decide. Because if I take too much aberration, then you will answer, of course, the geometrical approach is appropriate. And if I take too little, then you'll say, well, it doesn't make sense if you have only a point in there. The red circle represents the what the airy pattern would be. So if I have if all rays focus, because this system is stigmatic, the geometrical approach is not bad. So I took just the right amount so that you can't really decide. Both describe well the situation. For instance, here I took a spherical aberration with exactly lambda over 2. Lambda over 2 is too much with respect to the Rayleigh criterion. We said lambda over 4 is the maximum if I look in the paraxial plane. So lambda over 2 is too much, and indeed the Strehl ratio drops down to 0.39. This is the spot diagram. This is the point spread function that you would calculate, that you do calculate by Fourier transform. Well, does it look about the same size? The answer is yes. Okay. I mean, you can't see very well because the contrast is not good enough, but there is a small halo here. Okay. What about coma? Oh, yeah. So, what about coma? Coma shifts actually the maximum from where it should be to another position. So these two, so actually this at the center of the black circle should be where the image should be if the system were perfect, the paraxial point. And actually it would be there. Well, indeed the intensity is very poor here. If you want to find the maximum, you have to tilt a little bit. Add some of this u term, the u power 3 term, in order to find the maximum. The maximum is tilted, it's here. Does it look like, do you see a comet shape here? Well, yeah, you can see it looks a little bit like a comet, but diffraction tells you have actually semi-rings, okay? Something like that looks like truncated rings. Astigmatism. No, sorry. Astigmatism. I took lambda over 2. Well, I already shown this picture yesterday. The Strehl ratio drops to 16%. And this is what you get. This is the point spread function. This is what the spot diagram says. Well, this is typically the case where the diffraction tells you a little more about what's going on, because it's not really a symmetrical revolution. It's got globally the same size, but you can see it looks more like a cross than a sphere. Okay. Do you have questions at that point? No questions? So then I'm going to go to something more practical. interruption. Yep, it's coming. Okay, so the outline of this, what I'm going to say now, is the following. I'm going to study one by one and give as many examples as possible of simple optical systems that have third-order spherical aberration, astigmatism and field curvature. And each time, especially for the spherical aberration, my question will be, how can I improve the system from a basic system to a more complicated system so that I can kill this aberration? So, spherical aberration of the third order. This transparency summarizes all you should know about spherical aberration of the third order. We saw this already. This is the wave aberration with respect to the sphere that is centered on the paraxial image, and it's the P. It varies as alpha prime to the power 4, and A here characterizes the amplitude of the spherical aberration. Using the Niveaux relationships, you get the transverse aberration. And actually, since dy prime is equal to the longitudinal shift here times tangent alpha prime, what it means is that if you just Taylor expand tangent alpha prime, you get this distance here, L, the longitudinal, what is called the longitudinal spherical aberration, is equal to A alpha prime squared. Okay, what you should remember about spherical aberration is this picture. You see that rays are tangential to the surface where there is a particular accumulation of light. It's called a caustic. And you see here these blue rays are the marginal rays. And they intercept this caustic, which has a symmetry of revolutions, in this plane. So what it means is that if you put your camera here, well, of course it's a disaster. This is your spot. If you move it this way, at some point the spot is minimum. This plane is called the minimum scatter focus. And if you keep going this way, at some point you reach this point here, where the marginal rays cross each other. This is called the marginal focus. And if you keep going, you have less light and less light in the center, and basically you have a large brilliant ring all around. Okay, one can show that the position of this minimum scatter focus is quite, it is 3/4 of this distance. It's obviously wrong on my drawing here, probably because there is not only third order aberration, but also fifth order. But within the third order approximation, this here is equal to 3/4 of that. One can ask also the question, by the way, this is the minimum scatter focus where the spot is minimum. But where is the best focus? The other point, the one that maximizes the intensity. It's not there. It's actually halfway between these 2 points. Here. I'm not going to show it here, but one can do that.
So, is the intensity profile uniform or most uniform in the best focus?
No, not at all.
Okay.
Not at all.
Or in the minimum scatter focus?
In the minimum scatter focus, it is if you forget about diffraction. Because you remember that diffraction, basically all it does is that it brings rings all around. So if you look in real at the minimum scatter focus, you would see something that has actually rings, but these are diffraction rings. And but the spot diagram given by Osco would be flat.